Okay, so in our next section, we're going to talk about some of the generic properties of local area networks and Ethernet switching, and then we'll look at the actual configuration of this step by step and the different commands that we can use on the routers and the switches to figure out what's actually going on behind the scene in the network. Now, as I mentioned yesterday, a local area network, or a LAN, is basically a network that is going to span just a small geographic region. Like there would be a local area network for the hotel here, or there'd be a local area network for your single office building, or like your house. So the idea behind this is that if I have a very long connection, like let's say between New York and Los Angeles, that would be categorized as a wide area network, because generally I need to talk to some sort of service provider in order to get my data from one point to the other. But if I'm in charge of managing all the routers, all of the switches within the single network, generally that's what's going to be categorized as a local area network. Now, a lot of the times the local area network also means an Ethernet LAN or an Ethernet local area network. The terms are technically mutually exclusive, where there are other protocols that can be used for LANs, but most of them are going to be obsolete at this point. Like some of the traditional protocols were like ATM, which is the asynchronous transfer mode, or the fiber distributed interface, the FDDI, or like token ring. There was an original IBM specification. But pretty much nowadays when anyone talks about a LAN, they're talking about an Ethernet network. So the typical switches that we plug into, like a Linksys router, that's going to be also an Ethernet switch. Now, we talked about some of the components of networks yesterday from just a general overview point of view, where, of course, we're going to have the physical connections in the network, like the actual cables, the connectors that are going on there. And in the case of Ethernet, usually this is going to be copper cabling, like these Category 5 cables you see that look like phone cords. Or it could be fiber cables, depending on how long the connection needs to be. Like some fiber cables can go up to a couple miles in distance, where the copper cables usually are going to be somewhere around like 300 feet or so, about 100 meters. Now, the difference in the cables, when we're looking at like Category 5 versus 5E or 6, these are defined by physical layer 1 standards that say like how many times should the twisted pairs be inside of the cable. A lot of that stuff we don't really need to worry about the specifics of. From our point of view, as long as we can get the basic layer 1 cabling working, then the rest of our side of configuration is going to be from layer 2 and beyond. So pretty much if you plug the cable in and you get a link light, then you know that the physical layer 1 cabling is working. So this would also be like our Ethernet NIC cards. Basically, when you plug into your laptop or plug into your desktop machine, you're plugging into your network interface card or your NIC card. So a NIC card is also going to be part of the Ethernet network. So we could categorize that as both a layer 1 device in the OSI model and a layer 2 device, because it's running as part of the physical network. Again, if we look at what we call here the peer-to-peer communication, or from the application on one machine all the way over to the other one, the Ethernet NIC card is going to run down here at layer 2 and layer 1. So layer 2 at the data link, this is where Ethernet is going to sit. And then layer 1, this is going to be where our actual electrical signal is. And the electrical signal is going to be the actual bits, the zeros and ones. So this then is going to be the first part, the actual physical connections of the network. The other portion that we're going to look at is what are the devices that make up the layer 2 network, or the Ethernet in between the hosts. So if I'm trying to get my traffic from this machine A over here on the left to this server B, it's probably unlikely that there's a physical cable that's running between these two. There's going to be some devices in the middle of the network, whether these are switches or whether these are bridges or routers. There's some devices that are physically sitting between point A and point B in the network. And in the case of Ethernet, we can put these into 4 general categories, where the first of which is a repeater, second is a hub, third is a bridge, and the last one is a switch. Now, the first of these 3, the repeaters, the hubs, and the bridges, at this point, pretty much these are obsolete. and they're all going to be taken care of by the functionality of the switches. But historically, what the hubs and the repeaters were used to do is essentially just extend the range of the cables. Where if I have host A that's trying to talk to host B and they're more than 100 meters apart, the problem with the original specification is that the cable couldn't go that long. So when I send my electrical signal out on one side, the other side's not going to receive it because there's not enough power in the cable to actually get there. So this was one of the main things that we use repeaters for, is basically just to extend either the electrical distance, or in the case of fiber optics, you could have layer 1 fiber repeaters that basically take the optical signal in, or the light in from one side, and then just send it back out the other side. Now the hub basically does the same thing. The difference is that the hub just has more ports. So where traditionally a repeater would have one interface coming in and one interface going out, where if I had these two hosts, host A trying to reach host B, I could have their physical cable go to the repeater. This is going to take the signal as it comes in from A, essentially amplify it, and then send it out the other direction towards B. But the disadvantage of this is that you can only now have 2 machines connected because there's only 2 ports on the repeater. So essentially this is what the hub was designed to fix, that we want multiple devices to connect to the network. So we can use it to add more connections to the local area network or to the LAN. Now the device still uses the same basic principle, that when the signal comes in, the only thing we're doing is just amplifying it out the other interfaces, or essentially repeating it. And the reason why that we wanted to do this is that the original specification for Ethernet, the devices were sharing the same physical cable, where along the path, as I mentioned yesterday, when you look at Ethernet from a logical network design point of view, usually you'll have this line in the middle and then these machines hanging off of it, because from the original specification, this was actually one physical line that ran through the network, and then these machines had their network interface cards, and they plugged directly into that single cable, and then it was shared end to end. So the idea with the hub is that we don't want to have to share the same physical cable throughout the whole network. So I could replace this then with a hub or with a repeater, and then eventually have multiple cables that are connecting the devices in the network. But the key is that for either of these, whether they're hubs or repeaters, they basically work at just layer 1 of the OSI model, because the only thing they're doing is just regenerating the electrical signal as it comes in. So if you think of like your cable TV, you can buy those cable amplifiers that as the signal comes in, it just repeats it as it goes out the other end, or makes the electrical signal stronger. Now the disadvantage of this is that typically the hubs and the repeaters are unmanaged devices, which means you just plug them in and then there's no configuration that goes along with them. So you can't do any type of customization, and it also means that these devices don't do any type of inspection inside the data before we send it out the other interfaces. So essentially it means that whatever traffic that comes in, I'm going to be sending the same traffic out all of the other interfaces. Now this also means that a hub or repeater, all of the ports are in what's known as the same collision domain. Now originally with Ethernet, since everyone was sharing the same wire, this physical cable was used both for sending data and for receiving data at the same time. So the issue they ran into is that if one host is sending at the same time that another one is sending, the electrical signals run into each other and they essentially cancel each other out, or they run into some interference. So the Ethernet specification came up with a way to prevent this, which is known as CSMACD, or Carrier Sense with Multiple Access and Collision Detection, which in a nutshell means that before you send traffic, you listen onto the wire to see if someone else is sending. And if you hear that no one else is sending at that point, then you can go ahead and send your traffic. But the disadvantage of this is that it means all of the devices are using the same bandwidth of the link. So even if everyone is connecting to the network with a 10 megabit per second bandwidth of the actual physical NIC card, they're sharing that 10 megabits per second against all of the machines. So if you have 100 PCs in your network, it means they all are sharing some portion of that 100 or that 10 megabit per second value. Now also we'll see that the devices connected to either a repeater or a hub are in what's known as the same broadcast domain. And this we'll talk about a little bit later when we look at the actual operations of the switches. But the broadcast domain basically means that if two devices are in the same broadcast domain, they can talk to each other directly by using the layer 2 protocol. So if host A and host B are in the same broadcast domain, they're communicating directly with Ethernet. Where we'll see later when we break up the network into multiple broadcast domains, they're going to have to communicate at a higher layer using layer 3, which is going to be for IP routing. But we'll come back to that when we get into more details with the routing topics. So in order to fix this problem, they came up with what's known as an Ethernet bridge. Now, an Ethernet bridge separates the devices into different collision domains. And as I mentioned before, the problem with the hubs and the repeaters is that everyone is trying to share the same bandwidth, or what we call contention. So they all have to listen. They run this contention algorithm that says, listen for an amount of time. If I don't hear anyone else sending, then I can send my traffic. So the Ethernet bridge is trying to fix this. And the way it does this is to separate the individual ports into separate collision domains. So it's an electrical function where when you're sending a signal on one side of the device, it's not the same signal that's on the other side, which means that the device now has to have some additional intelligence. So the key is that with a bridge, since the devices are in different collision domains, they don't share the same bandwidth. If I have 10 megabits per second on one side and 10 megabits per second on the other side of the bridge, then the individual host can use that full value. But it's still extending the range of the cable just like a repeater. Now, in order to actually get this to work, the bridge now needs to figure out who are the hosts that are trying to send traffic between its ports. So we could think about the bridge as if we had a connection between two portions of the local area network, where let's say that we have hosts A, B, and C on the left-hand portion of the bridge. Somehow they connect to this device, connect to the bridge, and then on the other side we have hosts D, E, and F. On this side here, it means that all of these three hosts, A, B, and C, these are in the same collision domain. So before A actually sends a packet onto the wire, it has to listen to see if B or C are sending at the same time. So only once it hears that no one else is sending traffic, then it can actually send the signal out. Same is going to be true on the other side, where D, E, and F, these are going to make up a second collision domain. So the advantage of this is that when D wants to send traffic, it only has to listen to see if E or F are sending, but not these three. Because the bridge is separating this as an electrical function where data that's generated over here is not automatically sent to this side of the network. But now the problem we run into is, what if A wants to send traffic to D? So how does the bridge know that when we send the data out, that it's actually going out this direction as opposed to going in this direction? And the way that we do this is by using what Ethernet calls the MAC address, or essentially the hardware address that is used at the layer 2 of the OSI model. So the MAC address, this is when you look at your end host, and if you look at the ipconfig/all, this hardware address, or the physical address, this is what they're talking about. So here there's an Ethernet adapter that has this particular MAC address, 000C, etc. But then there's also an IP address that is assigned. So we're now going to use two different sets of addresses, where this one Here the IP address is a layer 3 IP address. This one here is a layer 2 MAC address. And this is now what the Ethernet bridges are going to use in order to send the traffic between the ports. So essentially, when traffic goes to be sent, the Ethernet bridge first has to figure out what are the addresses of the devices that are on the LAN. So it needs to learn which MAC addresses are connected to which individual ports. Now once it does this, when traffic is trying to be sent, it is then going to choose which port I send it on based on the destination of the MAC address. And this is the reason why we say that a bridge works at layer 2 of the OSI model. So before it can send packets between A and D, so if I have my web server here on D, and my client is at A, when I try to send a packet in this direction, the bridge is going to look at the MAC address destination, and it's going to say the destination is D, and I know that D is connected on this interface. So then the traffic goes in that direction. Now we'll talk about the specifics of how does it know that the MAC address is on that port, and ultimately when we look at the switches, there's ways we can verify what are the addresses that these individual hosts are assigned, and how is the bridge or the switch going to decide when traffic comes in one port, how do we know to send it out this one versus the other one? But again, the key is that since we're trying to separate this into more than just an electrical function where we're sharing the same physical cable, the bridge now needs to have more intelligence, or essentially needs to work at a higher layer of the OSI model. Now, an Ethernet switch is basically the same thing. The difference is that a switch is just a multi-port bridge. Where in today's networks, it doesn't make sense that you have a switch with just 2 ports, where the cable comes in and then the cable goes out. So pretty much every switch is going to have 3 or more ports, where typically they'll have, for small ones, maybe 4 to 8, and then for the typical like enterprise access switches, they usually come in multiples of 12 or 24. Like a 24-port switch or a 48-port switch, and they go up from there. But the idea is the same, that the hub is like a repeater, where a repeater is just a hub is a multi-port repeater, where a switch is basically just a multi-port bridge. Now the key is that on the switches, each port is going to be in its own collision domain, which allows us to run the Ethernet network in what's known as full duplex mode. So I'm able to send traffic and I'm able to receive traffic at the same time, because when we look at this from a physical point of view, there's a different cable that's used to send versus a different cable that's used to receive. So if you look at like the actual connection of your copper cables, like the category 5 ones, you'll see it's actually made up of a series of cables inside of there, where some of them are using for sending the data, some of them are used for receiving the data. But the key is that now, since the individual ports are in their own collision domain, the devices don't have to share the same bandwidth. So if the switch is a 100 megabit per second fast Ethernet switch, it means that each host is dedicated to be able to send 100 megabits per second and be able to receive that at the same time. But just like the bridge, all the traffic is going to be forwarded based on the MAC addresses. So we'll see once we go to actually send data between the hosts, the switch in the middle is going to need to keep track of what are the addresses that all of the hosts have. And we store this in what's known as the MAC address table, or the CAM table, where the CAM table is the content addressable memory. So CAM, or content addressable memory, this is basically just a fancy way of saying where we store the MAC addresses. So in the case of iOS, we'll use commands like the show MAC address table, and that's going to show us what are the hardware addresses of all the hosts that are on that particular LAN.
Is CAM a term covered on these ends?
Most likely, yeah. So like the other 3 devices, the repeaters, the hubs, or the bridges, the Ethernet switch is also going to extend the cable range. So when you look at the actual specification, where Fast Ethernet may say that the range of this particular cable is 100 meters, It means that you could potentially have the network connected so that if host A has a cable that goes to a switch, and then from the switch we're going to host B, it means that on each of these runs, they could be 100 meters each. Because we're doing that same basic electrical repeating or regeneration of the signal. As it comes in, the switch learns the packet coming in from A. It says, look at the MAC address destination. If it's going towards B, then I'm going to regenerate the signal as it goes in that direction. So the switch is working at both layer 1 and 2 of the OSI model, where 1 is where the physical electrical stuff is going to be, and then layer 2 is where it's looking at the MAC addresses for Ethernet to figure out how it actually moves the data between the ports. So let's take a look at this within the scope of our current network that's set up. So this diagram shows a subset of the physical topology that we're using, where basically I'm just not going to be using all of the connections or not all of the cables for this example. But the idea is the same as before, where everyone right now is inside the same network, 192.168.0.0/24. Router 1 has the address .1, router 2 is .2, router 3 is .3, etc. So everyone has an IP address assigned, along with the switches. The switches here, switch 1 is .6, switch 2 is .7, switch 3 is .8, and then the Windows PC here is .100. Now we saw already that everyone has basic IP communication with each other, and we saw this by running the ping command. We ping 192.168.0.1. I'm able to reach router 1. I'm able to reach router 2. But we know that these devices aren't actually physically connected. So this means that when the packets actually come into the layer 2 switches, that they're going to have to make some decision to figure out how does the traffic actually go through the network. So this means that our ICMP ping that came in from the Windows machine, which ping is an ICMP echo, or an Internet Control Messaging Protocol, ICMP. So it's an ICMP ping comes in, and let's say that this is going towards router 1. Now before the switch can send this out, it needs to figure out, is this supposed to go in this direction? Is it supposed to go in this direction? Is it supposed to go in that direction? And the way it's going to know this is it needs to figure out what is the MAC address that router 1 has assigned. So essentially every Ethernet interface, whether it's on your laptop or a router or a switch, every Ethernet interface is going to have one of these addresses assigned. And normally this is going to be something that you don't change. You just leave whatever the default assignment is that the actual manufacturer put on there, because they're supposed to be unique when they're being created in the first place. Now we saw on the Windows machine that we can verify this when we look at the ipconfig/all, where there's different MAC addresses here for its different Ethernet interfaces. So we have this adapter that's inside, this adapter that's outside. Each of them have unique MAC addresses. So these values here, the 000C29, the first portion of it is based on the vendor. And most likely this is going to be some pool that's for VMware. On this portion, this is going to be some unique value that they're assigning, where when you put the two of these together, it always ends up in a unique number. So normally two hosts are not ever supposed to have the same MAC address. It's not impossible for it to happen, but it's not supposed to. And the reason why is that when the switch actually goes to send its traffic, it needs to know that router 1 has a different address than router 2 does, or than router 4 or router 3, because otherwise it's going to send the data in the wrong direction. So ultimately our goal here is that when the ping comes in, that the switch is going to send it just to router 1 and not to anyone else. So if we were to look at router 1 in either the router's iOS or the switch's iOS, we can see what the MAC addresses are if we look at the show interfaces. So show interfaces is going to show us different types of physical properties of the links that the routers have. So it's going to show all of its interfaces. It's going to tell us some of the stuff that we talked about yesterday, like what's the layer 1 status of the interface, which right now is up, and what the layer 2 status of the interface, which is the line protocol. Normally this should be up, up is what we call it, or up/up, which means there's nothing wrong with the physical cable, there's nothing wrong with the layer 2 protocol, which in this case is Ethernet. If you see anything else here, if you see up down or down down or administratively down, it means there's something wrong with the interface and you're not going to be able to send traffic on it. We see this when we scroll down a little bit further on this serial interface that would be used to connect to the WAN. Right now it says it's administratively down, which means it has what command configured? The shutdown command. So we disabled it in software. If I were to go to this interface, so I go to global configuration with configured terminal, go to interface serial 0/0, and I said no shutdown. Then look at the result of the show interfaces. The serial link is no longer administratively down, but there's still something wrong with it. It says the link is down and the line protocol is down, which means there's both a physical layer 1 problem and there's some sort of layer 2 problem. Now for serial interfaces, we'll talk about this more when we get to the wide area networking protocols. But for Ethernet, you really shouldn't see anything else besides up, up. If it says up, down, usually this means that there's something wrong with the other end of the link. So if I were to go to the switch that router 1 is connected to, and this is on interface fast Ethernet 0/1. If I were to go to interface fast Ethernet 0/1 and issue the shutdown command, what I would see on router 1 is that router 1 should get a logging message here that says the line protocol of the interface is down. If we look at the show interfaces again, it says my physical cable is fine, but there's something wrong with the Ethernet protocol. Where again, in the case of Ethernet, if the link is up, down, usually it means it's the other side's problem. We would also see this if we looked at the show IP interface brief. It says the link status is up, but the protocol is down. So before we try to send any traffic into the Ethernet network, we need to make sure that the status says up, up. This would verify there's nothing wrong with the physical cabling, and then that both of the links are actually enabled. If I say no shutdown, router 1 should get another log message that says the line protocol changes to up. Where if I show IP interface brief, now the line status is up, the layer 1, and the protocol status is up. So now I know we're ready to actually send traffic into the network. If we look at the show interfaces again, this is going to show us some of the other properties, like what is the hardware address, which here, this is the MAC address. So router 1 has this address 0011BB A4BC20. Now you generally don't need to memorize these addresses for any reason ever. This is one of the reasons that we use the layer 3 IP addressing as opposed to the MAC addresses, because these addresses are really long and they're in hexadecimal format, which means you'd have to know the numbers plus the letters A through F. So usually we don't really care what the value is. Only the switch is going to care what that is. What we normally want to know is what is the layer 3 logical IP address that we assigned. But let's go ahead and make a list of what these addresses are. So router 1 on fast Ethernet 0/0, this is 0011.BBA4BC20. And we'll do this on all the other routers as well. We'll look at the show interfaces. This is router 2's address. And they're going to be different for the different physical interfaces. So fast Ethernet 0/1 is going to have a different MAC address than fast Ethernet 0/0 would. Router 3, if we show interfaces, router 4, then on router 5, I'm using fast Ethernet 0/1. So on router 5, I could either say show interfaces, or I could specify which one I want to see. Show interfaces, fast Ethernet 0/1. If we were to look at show interface fast Ethernet 0/0, you can see it's one digit difference, where fast Ethernet 0/0 is 001121C90860. The next one is 61. So we're always going to have a unique value for these. Now you'll see the router shows two different addresses. It says this is the MAC address, and then the BIA, or the burned in address, is this value. By default, it's going to be the same. But the reason it shows you this is that it's saying the burned in address is what was assigned by the manufacturer. So when whoever made the actual interface driver for like the chips on the actual interface, they gave it this address. This is the one that the router is currently using, which in this case is the same, but the reason they show it twice is that I could change this one if I wanted to. So I could go to the router's interface and say, on interface fast Ethernet 0/0, I want a new MAC-address. And I could set this to be whatever I want, 5555, 5555, 5555. Now there is a specific format that it has to conform to. But if I were to say, let's start with 0011, that should be valid. Then 5555, 5555. You can change these, you can see, and if we look at the show interfaces, we can see now it has a different value than what it was burned in. There's not many cases where you would need to do this to begin with. So you technically can change it if you want to, but we don't really care what it is. Because the only device that really cares what the MAC address is the layer 2 switch. Now you can end up in some very obscure scenarios where the vendor could accidentally assign the same address twice. And I have actually seen this before, where one network card on one host has the same address on the other one. And the result is that neither of them are going to be able to send traffic into the network. Because the packet comes in, and then the switch says, I'm supposed to go this way to get there. Then it hears the same address come in a different interface and says, well, now that address is over there. So it flips back and forth, and then the end result is that neither of them are able to get on the network. So you could theoretically change it to get around with a problem like that, but you're not supposed to run into that. The vendor is supposed to use a different burned-in address for every single Ethernet card. Okay, let's also look at the switches now. For switch 1, switch 2, and switch 3, this MAC address is going to be on its VLAN interface, which is this is VLAN 1. And in a little bit, we'll talk about specifically what this means, the virtual local area network, or the VLAN. But on switch 1, when we look at the show IP interface brief, this is the interface that I assigned the IP address on. If I look at the show interface VLAN 1, there should be a unique MAC address. So this is switch 1. Then switch 2 is going to have the same VLAN. Switch 3 is going to have the same VLAN. If we look at show interfaces VLAN 1, and then lastly on switch 3, show interfaces VLAN 1. So now we know what are all the layer 2 Ethernet MAC addresses of the end hosts. What this means now is that when the layer 2 switches in the middle, which are switch 1, switch 2, and switch 3, when they go to make a decision when data comes in and is trying to go out to some destination, so let's say that ping that came from the Windows machine, the ICMP echo came in, it's trying to get it over to router 1. It looks in that local table, which is called the CAM table, the content addressable memory, and it does a lookup and says, what's the MAC address that's inside this packet? So the host to begin with, it's going to know what the MAC address is of router 1. So it says, look at the destination that's inside the layer 2 Ethernet header and figure out what port that's located on. And on the switch, if we look at the show MAC address table, and I'm going to add some other options here. I'm going to say the dynamically learned ones specifically for VLAN 1. And the reason I'm adding that argument is that there's a bunch of other MAC addresses that we don't need to look at for this example. But here it has a list of all of these addresses and what are the associated ports in order to reach them. So if we correlate this against this list that we have, all of the devices' MAC addresses should be somewhere in this list, where it's saying that on this port here, Fast Ethernet 0/13, this is the interface that is using to reach router 4. Where router 1, 0011 BBA4, this is located on Fast Ethernet 0/1. Where here, this interface, this is the one that we see in the diagram. So switch 1 knows that when I want to send traffic to router 1, it's supposed to go out this interface. If I were to send traffic to someone else, to router 4, it says the link I'm using there is this one that ends in F5E0. F5E0 is on Fast Ethernet 0/13. So it's a link to one of the other switches. Now at this point, we don't really care how it learns the addresses. We'll talk about that in a little bit. But the key is that ultimately the switch is going to know what are all the MAC addresses of all the hosts on the LAN. And this is then how it decides when a packet comes in and it's going to this particular destination. The only thing I need to do is move the packet out that link. So it's not going to make any changes to what the data looks like. It's just going to take the original frame that comes in. It says this is the destination. It's then going to send it out this particular port. If we were to look at the other switches, let's say on switch 2 and do the same thing. If we look at the show MAC address table, this is going to show the full table where a bunch of these are reserved values like for the CPU itself. We don't really need to be concerned about what these ones relate to. But there is, on VLAN 1, these addresses. If we show MAC address table, the dynamically learned ones from VLAN 1. Somewhere in this list essentially should be all of the addresses. Where router 1's address 0011BBA4BC20, it says I'm going to use Fast Ethernet 0/13 to get there. If we correlate this with the diagram, we can see this is the physical port that's plugged into switch 1. So if we were to look at packets that are moving between those two hosts, between router 1 and router 4, it means that 1 is going to send this to switch 1. Switch 1 is sending it out this port here. It's going that direction. Switch 2 says to get to router 4, I'm using that one. Then on the way back, the traffic is going to follow the same direction. But the advantage of this is that it means it doesn't take up bandwidth on the links between switch 1 and switch 3. Or router 5 doesn't have to be concerned with that data because it's only moving between these two individual hosts. And in the case of IP traffic, this is what we call a unicast communication. So unicast means it's coming from one source and going to one destination. So it's a one-to-one communication between them. When we start to look at the details of the layer 3 IP addressing and how the devices figure this out, there's a function of IP that is known as the Address Resolution Protocol, or ARP, where when the devices want to send traffic to each other, the router needs to know what's the MAC address that corresponds to router 4. Because the layer 2 switch in the middle, the only thing it cares about is what? It only cares about the MAC address. But the router is a layer 3 device, so it needs to know what's the correlation between the IP address and the MAC address. If we look at the show ARP for the Address Resolution Protocol, router 1, when it wants to send packets to other destinations, it's going to keep this mapping table between them, where it says this address, this is my local address here, this corresponds to my hardware address, my MAC address. If I were to send a ping to router 4's address, when this packet was being dropped, this is where router 1 and 4 were trying to learn each other's MAC addresses. So the first packet goes into the network and it gets lost because they didn't know where to send it yet. Eventually they learn this and then the packets go through. We can see this now when we look at the show ARP again. It now knows that for this address of router 4, this should be its MAC address. When we look at the result of the communication, router 1 was sending the packet from 1 into the switch. When it comes from the ping application, which remember is working at layer 3, router 1 is going to have to do the encapsulation of it, which means it's moving down the layers of the OSI model. So router 1 says that there's the ping that I'm trying to send. On top of this, I'm going to add a layer 3 IP header that says the destination of the packet is router 4. So in this layer 3 header, it's going to say this is going to 192.168.0.4. It gets down to the layer 2 process. The layer 2 process says when I send it to the switch, the only thing the switch knows is the MAC address. So I need to add this information to the packet. Whatever the MAC address then was of router 4, router 1 is going to add that. So it looks up basically in this mapping table, it says 000F2442 F5E0. This needs to go in the layer 2 header, the MAC address. So now when the switch receives it, the switch says, look in the MAC address table, show MAC address table dynamic VLAN 1, find whatever address matched router 4's, which again is this one, 000F2442, this one here. I now know what port that needs to go out. It needs to go out fast Ethernet 0/13. So now it goes this direction. Switch 2 gets it, and it's going to do the same thing. Switch 2 says, show MAC address table, look at the specific address of this one. And this is what it's doing behind the scenes. So it says, look at that address. It turns out that this is located on port fast Ethernet 0/4. So now I know that the packet needs to go in that direction. Now router 4 got the packet from 1. 4 is going to try to send its ping reply, where ping is made up of 2 packets. One that comes from the source to the destination saying, are you alive? And then the destination reply says, yes, I'm here. I'm running IP. So router 4 on the way back is going to do the same thing. If we look at the show ARP, it now has this correlation. The fact that the address of router 1, the IP address of router 1, corresponds with this MAC address, 0011BBA4BC20. So it builds its reply. In the layer 3 header, it says it's going to 192.168.0.1. In the layer 2 header, it says it's going to 0011BBA4, etc. This then forwards out fast Ethernet 0/0. It gets to switch 2 that is attached. Switch 2 says, look for this new address. That points out fast Ethernet 13. So now the reply is coming in the opposite direction. It goes from 4 to switch 2. Switch 2 says it's out this link. So it goes to switch 1. Switch 1 likewise does the same thing. It says find that address. This points out fast Ethernet 0/1. So it sent out this interface to router 1, and then the pings are complete. But the key is that for every packet that goes from the source to the destination, it's happening individually for each of them. So for each ping that router 1 is sending, the switches are looking at the layer 2 address and figuring out what port is it supposed to go to. Then when it gets to the destination, it's coming back. The destination changes so that it's going to router 1's MAC address, and the switches can send the packets in the reverse direction.